DraftScience video. Yes, another one. Electricity this time. So I was thinking about solenoids, coils of wire, and there's lots of subtleties involved in function, what it does electrically, inside and outside the coil of wire, progressively coiled in a direction. That overall the coil turns into a magnet, which is sort of interesting. If you detect the field inside of it, you'll find out it's, like a magnet, north-south kind of ends, which is interesting. But that's like the voltage argument, that voltage is intrinsically polarized. So that got me thinking about, they always talk about monopoles again in the absence of a magnetic monopole. There's really an absence of an electric monopole. It's sort of a deception in a way, because the electrical circumstance is in a sense always connected to a pole. It's just that it's like the two ends of the pole and nothing in between. It's the conduit, the conductor is always sort of invisible, can be invisible. It is invisible, and certainly when you think of a little lightning and breakdown voltage, as they call it. The poles are quite obviously existing. They're just separated by a great deal of distance. So it's a very long magnet, kind of a thing. Can be. Certainly in space it would be. I don't know what the breakdown voltage in space is, empty space, or I'll have to find that out sometime or other and do some more figuring. But there's this idea of you move two, you take two charged plates and you move them apart, and the voltage between them gets bigger and bigger and bigger. And eventually you'll get to some breakdown voltage where you'll just basically lose your charge to ground. So there is, in a sense, no monopole, because all you have to do is create enough voltage to break it down, and it'll be obvious there won't be any pole. But like I said, it's not real. There's no such thing as really a monopole in electricity. It's sort of an illusion. There's always a conductor. They sort of feed on each other. But anyway, that's not really the subject of this video. So, alright, so we'll do this, try to do some of this in pictures, just to make it more visible and understandable, perhaps. So we'll just draw a standard conductor, which we'll call this a standard conductor. It's just, and you put a voltage over here, so that would be a minus, say 150. I don't know why I like that number, but I do. And this is, say, just a ground, neutral. So when you initiate the voltage, what's really happening? Well, you have this whole reservoir of wire. See, it's a whole reservoir of wire. And actually, the 150 volts can travel from here to here, can go this distance, only using a small portion of this conductor, depending on what your draw is, your current. So depending on how much of a short you have to the other end of the battery, and how powerful your battery even, will dictate how much current it can possibly push through a wire at one time. So there's not so much, it's not so much about the voltage as it is the capacity to keep producing that voltage, at that pressure. But anyway, the point would be is that this is almost, I used the word in the Hoffa response video previous, of reservoir, and that's what it really is. It's an empty reservoir, and that the part of the wire that'll actually have current in it can end up being very small when you're continuing to draw the current. So in a sense, when you first initiate the voltage, it will fill the entire reservoir. It will be a very large current, a very big I will be created in the initial milliseconds, because the voltage will move across the entire conductor. It'll fill it entire, every bit of a pathway it will take to fill the whole thing. And then you'll end up with like a reservoir. So say if I had a reservoir was full of water, the reservoir just ends up having a little stream going through it to the out, right? So it can have a huge, depth, hold a huge volume of water, but there's only, 1% of the water coming in and 1% going out. So it's only a small path that actually has movement in it once it fills. So once the reservoir fills, then it's only a small part of it that's moving. So in the coiled example, you have this phenomenon where if I put a voltage across this of 150 volts, and I don't pay attention to that initial millisecond, there's very little field here. So if I'm just running 150 volts through the resistance of the wire, let's say the wire has enough resistance in it not to burn up the battery, and so it travels through here, what's happening is this ends up becoming, well, traditionally this would be like I say, I have to go with a negative 150 just to make it understood, that this is your neutral, not your positive. But anyway, this will end up being, your south and north pole of your battery. Of your magnet. That half of it will be magnetized interior, just like a battery. Half the south pole, half the north pole, in terms of the polarization of the field inside. And the field outside will seem like zero. It's not absolutely zero, but it's this tiny little field that you have radiating outside the coil. So you have a strong field inside, relatively strong, and you have very little field outside. And so that's sort of the thing I was thinking about, and why is that happening? Because theoretically, I would argue that the polarization goes in, it gets polarized, it comes out, it gets polarized, so there still should be stuff coming out that's polarized. But there's a couple of tricks. Well, first off, so the first thing to understand, though, is that there is a strong field, magnetic field, for those first couple of milliseconds. When this voltage first starts filling all this wire, so when it starts filling the entire wire, then it has a high current, and it's got a high field. And then it drops off really quick because only a tiny bit of the actual conductor will be drawing current. So only a tiny stream inside the reservoir is still moving. So the trick with conductors that make them different than magnets is that their configuration, let's say this is what they look like polarized, and that, this is what they look like unpolarized, lines going in all kinds of directions. This is the state they really want to be in. And this is the unnatural state. So when the current's moving, it's doing this. It's polarizing all the electrons, all the atoms. And in the part where it's not moving, it goes back to this neutral state. So essentially the reservoir, as soon as you get past that first millisecond, this starts degrading back into a mixed state. And the only part that's now polarized is the part where the current's actually traveling through the conductor, the amount of current. And so the rest of the wire is going back just to being a normal wire. And the only part of the wire that's relevant to the polarization is the part that still has current moving in it. So it's only in the moving state where electricity is actually moving through that it's able to maintain the straight line, so to speak. What's the right word to say for that? Something like that. But it really has to do with this initial amount of pressure, and the pressure, how quickly it diminishes. So the quicker the voltage can fall off, the less this effect of refilling the reservoir, and the less field you'll get in that initial moment. So it still has to do with how much your battery can produce. If your battery can't produce enough voltage to hit a maximum current, then you won't fill the reservoir, and you won't have as high an EMF at those initial milliseconds. But it will test the capacity of the battery when you first initiate the voltage. So when the switch is first thrown is when the voltage first leaves, and it just depends on how much crowd there is behind it. And sometimes the voltage can read a high voltage, but there's very little crowd. There's very little density to the voltage. So if the voltage doesn't have any density behind it, then it will dissipate quickly. So anyway, so when there's a standing current through this coil, what's really happening is only a small part of the coil is polarized. And the trick is that if you look at it, a cross section of the coil, the part here is bent. So you see, so if you think of it as a conductor, back to the the conductor argument, a thicker thing. So this is the coil. You can see that this distance is much shorter than this outside distance. So obviously the current takes the shorter distance first. I mean, not obviously. Somebody could say because why? Well, because it is all repulsive. It tends to go to the outside, and clearly it's going to go to the outside where it's going to get to the destination the quickest, or where the funnel's pulling the hardest. So, in a sense, there's more ease of flow here, and that's why it just all migrates to the stronger flow. So the stronger flow is in here, and that's everything gets sucked into like a vortex gets sucked into the stronger flow, you could argue. So that might be the because why thing. But clearly the shorter distance is the simple answer, and that shorter distance would be preferable. And so the current is running on the inside of the wire. And so that's why when the field goes through, it goes through a non-polarized exterior, right? And it only gets polarized here. And so it polarizes this interior, and that's why you have a high magnetic field in the interior, because both the gravitons coming from all the sides, let's say, they're all polarizing on this interior, right? And all the stuff coming through the interior, going back to the outside, is going through this mixed thing here, so it's getting depolarized as it goes out. So there's a great deal of depolarization taking place because it's going through matter that has no polarization on the surface. And again, the fundamental argument here is that what causes polarization is what the last thing you went through is likely to be your polarization. Obviously density and a lot of other things have something, not obviously, but density would have something to do with it, but it's really about the surface, the last surface you go through. If it's a polarized surface because it has charge on it, then that surface will be your identity. And so like you get polarized, get unpolarized in here, then get polarized again. So the tendency is this matter that doesn't have current in it, a conductor that doesn't, the part of the conductor that doesn't actively have current in it is depolarizing, while the part of the conductor that does have current in it, that has electrons moving, is the part that's polarized. So it's only where the electrons are moving that the polarizing filter exists. And as soon as they stop moving in a direction, I mean, jiggling isn't the same as moving. Jiggling is non-polarized. Moving in a direction is when they have to line up. That's when they do their thing, polarizing thing. So the conductor only creates polarization for the part of the conductor that has active voltage moving through it, actual electrons migrating. That's when the polarizing filter exists, and it doesn't exist any other time. So that's why alternating current works, is because it keeps the stream flowing all the time. And it empties the reservoir, so to speak. So it always tests the current to its maximum, because as it switches direction, it cleans any polarizations out of, especially, we're back to that whole blocking thing, but I don't want to get into the coil of wire, but how it would end up blocking a little bit of itself. This is always a problem. Is the current moving this way here, and it's moving this way here, and those are obviously opposite directions. And so the trick is that this is going to stifle this voltage, and this is going to stifle this voltage, and this is going to stifle this voltage, and so it does have a little bit of an inefficiency in the voltage getting through the wire, and so there needs to be a density to the voltage for it to continue to push through the wire. Yeah. So what else did I want to get to? But yeah, the really key thing for me, the realization that makes it, that explains why the absence of the field on the exterior of the coil of the solenoid is because the current's running on the interior of the wire. So that was the new revelation. And the second new revelation, I suppose, is the fact that the polarization only exists in the portion of the conductor that actually has moving voltage through it. Obviously, a conductor, if I made a wire this thick and then I, ran a 10-watt light bulb, this wire would be much thicker than is needed to transmit the electricity. So only the 10 watts of voltage, only the density of voltage needed goes through this conductor. So it's only a tiny piece of the conductor that would actually be actively migrating electrons, and only that piece of the wire is polarized. And so the key is how is the polarization conveyed on the wire? And the point would be is it's conveyed on the exterior usually. But if you bend the wire, then you create an interior that's a shorter distance. And it'll tend to move on the interior then. Yeah. What else? So initial current is as high as the source can produce. And the steady state voltage is just what is demanded in terms of the wattage, and so current can drop quite a bit. And so it's a reservoir that empties, and let's see if there's anything else. Let's see. Polarizing filter is only maintained as long as the current is maintained. Yeah. Right, so the difference between an electromagnet and a magnet is just the fact that you need the electric current to be moving to create the magnetized structure. And the magnetized structure goes away as soon as the current goes away. Yeah. Pretty much. Yeah. Unless you induce magnetism, unless it's a magnetic conductor, steel wire or something, iron wire, and then it might become magnetized on its own. It might stay magnetized. Yeah, so that's enough, I think. I don't think I need to beat it to death. So, just making it more solid. I mean, you can just go with all these subjects. You can go into a great deal of depth in terms of trying to analyze all the special circumstances you can create, and I think that's all very fruitful and interesting and fun. I wish some other people would participate in it. Me having to do all of this discovery. You're all missing out on discovery. But that just, I think, shows the depth of this explanation, is that every time I have challenged it, every time I've thought of something and said, oh, that doesn't fit now, I've always found a fit. So, like I said, I think that just is further demonstration of the strength of this fundamental theory of particle force, and then recognizing polarization as a way of magnifying the particle force. A very simple premise. First, it's particles, it's photons, it's tons that are creating the pressure, and that the pressure can be minimized or maximized based on polarization. Two fundamental, little simple concepts, and with tremendous depth in terms of making it understandable why almost everything that happens physically happens. So, yeah, it's really good stuff. Now I have to write it some more. I just really hate writing. I gotta do it though. I gotta get this done. I just want to get this you know, this is the revolution. It's in the book. It's already written as a historical. This will be the historical truth. This will be the thing that will be the future. This is what the future is going to understand about the mechanics of physics. And here I'm sitting there knowing, I can sit there looking at the crystal ball thing with the future, and I'm saying, well, gee, can't we just jump ahead to there? Because this is obvious, right? I shouldn't have to do any more than I've already done, right? I've already done enough. This is it. This is the answer. People are going to force me to drag you to the future. Pain in the asses. So anyway, till next time.